Greetings, friends, fellow Earthlings, and fellow producers of biosignatures, and welcome to Ask An Astrobiologist, the show that celebrates the science and celebrates the scientists involved in our quest to understand the nature of life in the cosmos. I'm your host, Dr. Graham Lau, and we're brought to you by the NASA Astrobiology Program and SegaNet.org. And this show is going to be really, really groovy, folks. We're going to talk about asteroids, agnostic biosignatures, experimental rock opera, and way more. I mean, it's episode 42, right? So we have to discuss life, the universe, and everything, or very nearly everything. But before we get into our featured guest today, we have our usual housekeeping to do to show some love to those of you out there showing us love and sharing information about our show online. Retweeting us, liking, getting involved in the conversation about our guests, about their research, the things they're doing in the realm of astrobiology. This month, we'd like to highlight two ambassadors for the show. Denise, who is always very active in sharing about Ask An Astrobiologist, and this month, a new ambassador, Aranava Padar. These two Twitter users have shared a lot about our show. They've gotten involved in the conversation, and we really, really appreciate that. It helps us to show our guests how much we care about what they're doing in astrobiology from around the world. Now, that said, I get the pleasure of introducing our guest for this show, Dr. Heather Graham, who is an organic geochemist and a research scientist at NASA's Goddard Space Flight Center. Dr. Graham's research focuses on the scientific development of tools and techniques that can help us identify agnostic biosignatures. She's involved in work for sample return missions from an asteroid and Mars. She's a member of the Laboratory for Agnostic Biosignatures, as well as for the Network for Life Detection. And she's also an experienced communicator of science, having even co-wrote and directed an experimental rock opera about hidden figures Katherine Johnson, Mary Jackson, and Dorothy Vaughn. I'm so excited to have her on the show. Dr. Graham, welcome to Ask An Astrobiologist.
Thanks, Dr. Graham. It's great to be here.
Yeah, just before the show, we were talking how some folks, they prefer to mention doctor and then first name. And so for some people out there, this is Dr. Graham talking to Dr. Graham on today's Ask An Astrobiologist, which I love. So Heather, one thing that I love to do with all of our guests when they first come on the show, since we do have some younger viewers very often who want to know how they can become astrobiologists and what pathways are available to them, I'd love to hear if you have a science origin story and what kind of drove you on your mission to earn your doctorate and become a researcher in astrobiology.
Yeah, I love talking about this because I'm hoping that when people hear about my science origin story, they can understand that it can happen at any point and it's not a singular event for a lot of people. For me, I actually didn't go to college until I was almost 30 years old, which, I'm not telling any students out there that this is license for you to quit school and go off and enjoy other pursuits. I don't want to get angry letters from your parents. But I just had other pursuits that I was interested in when I was a young adult. And when I think about my interest in science, it didn't necessarily come from school. It came from just observing nature. And I lived in the woods growing up, and my parents they didn't have answers for me a lot of times, but they would take me to the library. And so if I found a weird thing on a stick, they would take me to the library, and I'd find out it's an insect egg case. And, what's that strange hole? Let's dig down there and see what horrible, snake we just unearthed and things like that. So for me, science and a science origin story is really embedded in the observation of nature. And I like to tell people that because everybody can do that. Maybe you don't have access to a great chemistry library or laboratory in your high school or wherever you might be at, but you can observe nature. And even if you live in a city, there's nature all around you. It's creeping up out of the cracks in the pavement. It's living on the bricks of your house. And if you look close enough, you'll find life everywhere and you'll find nature there. And it thinks of us as its habitat and its pursuit as well. And so that's how I think of my origin story, is just looking around at the world. And then eventually I formalized that by going to college a little bit later than a lot of people would have.
Oh, I love that so much. And like, I have a young child at home right now, and I watch him when he just like interacts with the world, and I see that curious scientist nature. You know, as Mary Wojtek says, everyone is an astrobiologist when it comes down to it. And so I love that. You know, it's the curiosity that drives you. And I appreciate that. You know, you have this slightly different story from some who went straight into college and then straight to graduate school and kind of did all those things right away in that usual pathway. There are a lot of other paths out there, and many of us have taken some non-traditional trajectories along the way. So, what was it about organic geochemistry that really drove you in that direction for earning your PhD in that field?
Yeah, so that's kind of funny because when I first started out in college, I actually went to community college, and I actually went to a community college for about 5 years. And part of that was because I just couldn't decide what I wanted to study. And at the end of 5 years, I'd taken literally every science class that was offered at Santa Monica College. And my chemistry professor, I loved chemistry, and everything always came back to chemistry for me. If I was taking a biology class, I wanted to relate it to chemistry. If I was taking physics, I wanted to understand the physics of those molecules. And finally, my organic chemistry professor, Dr. Jamie Anderson, sat me down and he was like, "We have no more classes for you to take. You're going to have to leave. You're going to have to be a big girl and go to another college." I was like, no. I'd literally taken everything, even field ornithology. And I think that I look back on that as being so pivotal and foundational for what I do now, because I have this breadth of knowledge that I was able to kind of have the time to synthesize into a grand vision of how nature, and when I say nature, I don't just mean life, I mean everything around us, the universe is nature, how that all works together. And so when I went to a 4-year school, Occidental College, I did want to focus on chemistry because for me, it was the language that all of nature was using to communicate with the rest of nature. And then when I started looking at going to grad school, it was really interesting because I wanted to learn more about evolution and the history of life in deep time. And so I started looking at grad school, and I thought I would probably study biology or study, go to botany or something like that. And everywhere that I looked was very contemporary and focused on scales of evolution that we can understand by looking at contemporary modern life. And one of my professors was like, I think you're going to have to study geology. And I was like, no, that's rocks. I do molecules. And that's how I learned about this idea of organic geochemistry. And for those of you who don't know, that's just the study of organic molecules that are preserved in the geologic record. So all of these biosignatures that are falling off of us and every other creature and slowly getting incorporated into rocks. Part of grad school was for me learning how to dig that back up out of the ground and learn from what those chemicals have now become, what life was like in the past.
That's so groovy. Yeah, and as soon as you said like rocks, no, I do molecules. The first thing that hit my mind is organic geochemistry is molecules and rocks, right? So that's really cool. You've had so many experiences along the way. You've been involved in science communication and so many areas of research, and you also have some really cool tattoos that we chose to ask our Twitter audience about online through NASA Astrobiology. There they are. And so we asked everyone, what do you think these tattoos are showing? And so we had a winner who didn't quite get it exactly right, but very, very close. Brian Halligan, user at Brian Halligan, said it was subatomic particle tracks from a super collider. Or was it the Higgs discovery? And so I think Brian threw out one or the other, maybe. But I'd love for you to share the story of your tattoos and the science behind them and why you got them in the first place.
Yeah, so a lot of my PhD work was actually studying light and the effect of light on ecology and plants in particular. What I really was interested in is when did plants develop the ability to live in energy limited situations? So if we think about deep, dark forests of the tropics now, there's all of these plants that are purposefully living where there's no energy. The sun is their energy, and they're competing at another level down in the bottom of those forests. But that's not how plants always worked. In the deep past, plants didn't have all of those layers. And I was curious, when did plants learn to do that? And why was it so late in their evolution? And it's around the time of the KT extinction that plants developed that technology to live in energy limited situations. So much of my thinking was about this interaction between light and life and energy and life. And so I told myself when I was in grad school, okay, my reward for working this hard is I'm going to get a cool tattoo to celebrate my PhD. And then, like with many people, when you get done writing your dissertation, you don't particularly want to memorialize it that way anymore because it just represents a lot of work. So but I'd learned so much about other forms of light. And if you read the information about this experiment, you're right, Brian. This is a particle collision experiment that was done in a bubble chamber at CERN at the Large Hadron Collider. It was called the UA5 experiment, and it was done in the 90s. And they were trying to crash together particles to make a particular kind of particle called the W particle. And what's really enticing and interesting about the W particle and how I got to it through botany and organic geochemistry is that this is a particle that we think might actually be something like a photon that had mass. And being an astrobiologist, you're constantly imagining, what is it like on other worlds? What would it be like to be a living organism on another world? What would you have to contend with? And that just blew my mind to think, what if your star was pelting photons at you that actually had mass? And it really made me rethink kind of how I think about photons from our sun and how glorious it is that they're not hitting me with any sort of mass that's, perceptible. So it just really blew away my whole thinking about what light was. And at the end of your dissertation, when you're so tired, to find a cool new angle on it is really wonderful. So I decided, yeah, that's what I'm going to commemorate. And it just means I have lots of conversations about particle physics at gas stations and in the grocery store. And then people will be like, oh, so you're a physicist? And I'll say, no, I'm an organic geochemist.
Oh, I love that crossover, though. Yeah, I have a tattoo for the SegaNet logo, which those who are watching on SegaNet can just look up to the top of their screen and see that logo. It's on my forearm, and it leads to lots of cool conversations about astrobiology and planets and life and all kinds of cool things. It's fun to add that kind of science ink to ourselves, as Carl Zimmer once called it. So after your PhD, then you got more involved in doing research in lots of kinds of realms of organic geochemistry, leading you to working now at NASA Goddard. I understand that you've been involved now in sample return missions with OREX, as well as for the upcoming Mars sample return. I wonder if you could speak to our audience about why sample return is so important, especially for an organic geochemist.
Yeah. So, there's this funny idea that we have about like, oh, we got to send rovers and orbiters and landers and things like this. But if you actually look at what we've done a lot of really well as space scientists worldwide is sample return. The many things that we brought back from the moon. We've had multiple comet and asteroid, or solar particles, small bodies that we brought back chunks of. And so it's actually something we do really well. There's a scientist at Ames Research Center, Scott Sanford, who did a talk for the University of Florida. You can find it online if you're interested. And he has this wonderful graph that he showed from a paper by Queenie Chan of all of the times we've actually gone out, left our planet and brought something back. So it's something we actually do good. And I'm really interested in it because, no matter how great we get at rovers and instruments that we put on spaceships, there's honestly nothing quite as great as the instruments that I have just down the hall from me here at Goddard Space Flight Center. We have so much more sensitivity and resolution, and we can actually manipulate samples so much better and actually prepare them in a way that we haven't been able to develop technology for yet, that there's just really no substitute for it quite yet. And so I'm really enthusiastic about sample return. And I also want to kind of make a connection between these two sample return efforts that I'm part of to get people thinking about other solar system bodies that they might not. I find a lot of people focus on planets like Mars and Mars sample return, because Mars, we can imagine being Earth-like and having life. But planets are really born as the kind of objects that osiris-rex is investigating, the asteroid Bennu. And that's the birthplace of so many of these organic chemicals that we think were part of early life. So if you ever want to really understand the origin of life, or actually agnostic biosignatures, where we're trying to really think broadly about life, you have to be able to understand that primordial material that's in those asteroids. So those are two really important kind of bookends for understanding astrobiology.
That's really great, and it really leads me to the next topic I want to discuss. But first, I do want to say Scott Sanford has been on our show. He was
Yay!
on the previous episode when we talked about osiris-rex. I wish I'd seen that graphic. I haven't seen it. I had to go and hunt down myself all of the different sample returns that we've done. So I would love to find that graphic and share it with our audience on Twitter and elsewhere.
Absolutely.
Yeah, I love this idea too, like Bennu and some of these other bodies, how important it is for us to understand, the primordial populations of these bodies that formed the planets of our solar system, and where some of our organic chemistry started in the solar system in cometary and asteroid materials. And also with sample return, as a geochemist myself, when I was earning my PhD, I did a lot of synchrotron based work. So X-ray absorption in these large particle accelerators, which you can't carry, this massive, trillions of tons of particle accelerator, across the solar system to Mars. But those samples, when they come back, there are folks who be using those kinds of high resolution techniques to really interrogate those samples, which is super exciting. But you also then transitioned us into our next topic, which is agnostic biosignatures. And honestly, I've been talking about them now more in my own conversations with people online. And I even know some astrobiologists who are still a little maybe fuzzy about what an agnostic biosignature is. Maybe they're agnostic and they're thinking towards what an agnostic biosignature is. I wonder for our audience if you could explain what are agnostic biosignatures and why is this kind of becoming a new realm of thinking in astrobiology?
Yeah, I feel like agnostic biosignatures, first people kind of have to struggle through whatever their definition of agnostic is before they can even get to the word biosignature and decide how they think those two things relate. But when we say agnostic biosignature, what we're really trying to say is a biosignature, a piece of evidence of past or present life that doesn't rely on any similar analogy to life on Earth. And, when I first say that, most people are like, are you talking about silicon-based life? And it's not even about that. It's about understanding what is the most basic general features of life that you can define and putting together a search pattern based on that for a biosignature. When we think about life, go even deeper, go even farther than silicon or carbon or things like that. What is the major thing that life is really doing? Life is harnessing energy and creating a state that is in disequilibrium with its environment. My body, your body right now, all of life around us is in disequilibrium with its environment. It's taking an energy and creating a chemical environment that is different than we would be that if we weren't life, where we're just basically going to go back into dust. And so thinking about it as an energy state might help people feel a little bit more comfortable with the idea of agnostic biosignatures. So when we're looking for agnostic biosignatures, we're not necessarily looking for, a microbe or some sort of creature like that. We're looking for evidence of a perturbation to an energy environment or to physics, something that tells us that there was extra energy in this environment that made this physical or chemical manifestation of past or present life. So that's the most general definition I could give. I hope that helps. If that's not helpful, let me know.
I hope so. Yeah, and I've heard you mention before that this is more about being like a physics detector more than being like a life detector for what we're doing right now in the solar system and even here on Earth for understanding life here on Earth. I mean, there could be some forms of life around us that we don't even know about here on our own planet for us to go explore. And so understanding, the energy, the information, and how that changes due to life, I think is a very important process. There's one thing I'd love for you to explain to our audience that I've heard about, and we mentioned before the show, you and I together, is the whiskey analogy that's been brought up in the agnostic biosignature realm. I'd love it if you could share that with our audience, since I imagine they'll enjoy understanding it through that analogy.
Oh yeah, this was actually refers to some samples that we actually analyzed, because whiskey is this amazing pastiche of a bunch of biological activity, and you can think of the fact that it's a whole bunch of starches that aren't particularly bioavailable, but were heated, and so there was this thermal component, and then it was given to a bunch of organisms, and they worked on it, and they produced fermentation, and they left behind in that fluid a bunch of the evidence of their metabolism, the metabolites that they make as they perform that fermentation. And then it's distilled. It's gone through this other thermal and physical separation process, which, if you were to imagine any sort of natural environment where that's happening, that would be challenging. Like, what's left over after you do that to any sort of fluid that once contained life? And then you sink it into a cask that's made of dead plants, dead life. But there's all of these leftover metabolites in that wood that are slowly leached into that. So whiskey has this evidence of life in terrible turmoil, life that went through a whole bunch of crazy steps, not dissimilar to what geology might do to evidence of past life, and then saturated it into a solution that's exposed to other molecules that came from life. So it's not terribly different than how you might think of life as it's being preserved in organic molecules as they're being preserved in geology. Whiskey is just this other slightly more enjoyable version of all of those same forcings on metabolites. And you end up having to analyze it and backtrack through, because there's nothing in there that's still living. By the time whiskey gets to your glass or my mass spectrometer, it's dead, but it has all of this evidence of these past organisms, from microbes to eukaryotes, still in that reservoir of information.
I love it. It's the things that biology has done, and then the transformations through time and through various processes that have occurred. And so, folks who are watching, next time you enjoy a glass of whiskey, maybe just hold the glass for a minute and let yourself think through that process. I would love to talk a lot more about agnostic biosignatures, but I do want to speak about a few more things with you before we open it up to the audience Q&A. For those watching, you can ask questions right now for Dr. Graham in the chats on NASA Astrobiology's Facebook page, or on Second Live, well, wherever you happen to be watching right now. If you're watching the recording on YouTube, obviously not live, but many of us do go in and check the questions there from time to time as well. Before we transition into the audience Q&A, I'd like to chat a little bit about some of the science communication work that you've done. For instance, I was very fortunate back in 2016 to compete in the national final of NASA's FameLab, or FameLab USA, in which you were a judge, and you judged myself and several others in our speaking. And you have, a great skill, a personality when you come to your science communication. You've been on NASA's Gravity Assist podcasts previously. You were on the Countdown to Mars features from NASA Astrobiology, and you've been doing a lot to share your science. I wonder if you could share a little bit of your vision for why we should share our science, and maybe even, what really drives you to share your science.
That's an interesting question, because I think there's a lot of different motivations and audiences that people think about when they talk about science communication. And I'm really reminded of conversations I had with the director of the rock opera that you mentioned I wrote, about some of the early mathematicians that were part of the Apollo space program, where she was asking me, like, what are you trying to get out of this script? Do you want people to leave understanding math, or are you trying to inform more about the players, the people in the story? Like, what do you want? And I think that's a really important thing to think about when you're doing science communication. Do I want people to leave this talk that we're having right now understanding particle physics, or do I want them to understand more about how science saturates our life? And that's kind of how I think about things. When I when I go to audiences, I want them to be able to realize that this thing that they're doing of observing nature is at its most basic level the business of science. So when you're observing nature, you are engaging in the world as a scientist does, only we do it with graphs and clipboards and, large whirring machines. But that's really what it's about. And so getting people engaged in rethinking what science is and how they are actually part of that activity and how they relate to those results is really what I'm trying to do when I talk to audiences. It's not quite like, oh, here I am a scientist, you can be one too, but just understanding what science is and how it's actually a really common and engaging natural pursuit for just about any humans. I bet your son's somewhere doing it right now.
I'm sure he's out right now on a walk somewhere in our neighborhood, checking out some bugs and doing some science. Even though it's a different kind of science, it's still that curiosity, that wonder, that engagement. And so I love that vision for sharing science. And I think communication is so important. And it's something that we really should be teaching, scientists and their learning and engineers and everyone really is how do you share what you're interested in, and when you're in love, you want to tell the universe, right? And so how do you tell the universe is a really important thing. And you mentioned the rock opera, and we want to talk about it, Determination of Azimuth. We had a small clip of it we shared on the NASA Astrobio Twitter account. And then we asked people online about which NASA mission was featured both in the rock opera as well as in Hidden Figures, in the movie of Hidden Figures. And we had potential to list Apollo 7, Apollo 11, Friendship 7, or Gemini 10. And interestingly, about 42% of the audience said Apollo 11, but the real answer was Friendship 7, everyone. Now, I will admit I've not read the book, nor have I actually seen the movie. I really have to catch up on my film watching. I'm like a decade behind on films, honestly, maybe even more than that now. But I'd love to hear more about the creation of this rock opera. What inspired you to share the story of the Hidden Figures of NASA, and to really share this in that format too as a rock opera?
Yeah. So that's a couple of great questions. I think the first thing to know about where I came to the inspiration is that when I was in grad school, I was part of a program that was funded by the NSF. It doesn't exist anymore, sadly. It was called the GK-12 Fellowship Program. And what they did was they took graduate students and embedded them in public schools that were underperforming in science. And so one day a week, I was at a middle school where I was helping the teachers there update their curriculum. I was running science clubs and, doing all these things that the teachers honestly don't have time to do because they're swamped. And, a lot of times these schools don't have enough money and they've got a lot of students and all those students are eager to learn, but there's just not enough teacher to go around. So that's where the NSF fellows really came in. And the school where I was at was largely African American. And so I got to talking to the teacher about okay, let's put together some curriculum for African American History Month. And she says, oh, no, we've got that covered. We always do something about George Washington Carver. And I said, oh, my goodness, he has been dead for a very long time. I think we have other heroes of science in the African American community that we can teach about. And so I started putting together a list of all of these people. And me being me and my interests, I was really focused on space science. And that's when I discovered the story of Katherine Johnson. And this was in, I want to say 2010. So no, maybe, no, 2013. Anyhow, it was a long time before the movie came out. And so I was just watching all these interviews of Katherine Johnson because she's been a hero in her own community for a long time and at NASA, but just not really known to the general public. And of all the stories that I looked at as part of that activity that I did at that middle school, Katherine Johnson's story just stuck with me and kept coming back to me. And I've been really involved in theater for a while. And so when there was this opportunity to pitch a short opera on any topic, I pitched the idea of a short opera about Katherine Johnson. And I love the medium of theater. I'm not, going to say anything good or bad about the movie. They don't pay me. But the medium of theater really gives you a chance to engage a whole lot of imagery and a whole lot of content in a much more deep and involved way than you can do in a movie where you're really relying just on keeping eyes on that screen the whole time. So in our show, we have simultaneous timelines of past and present Katherine Johnson. We have actors going out into the audience. Everyone in the audience had all of this paperwork that was, supposed to go along with the script. So it's this really engaging, interactive way of doing things. And when, like I said, I talked to the director, she's like, my goodness, there's a lot of math in this because all of the songs in the opera are taken directly from papers Katherine Johnson wrote. And so a lot of times the actors, if you guys go out and find this opera online, the actors are just singing equations, which, God bless them. What a horrible thing for a screenwriter, for a scriptwriter to do to them. But they're just singing equations. And I wanted to have that happen because that was Katherine Johnson's language. Just like when we watch opera in Italian, because that was the language of that writer and those people. Her language was math. And getting to hear singers just belting out math really felt to me like connecting with what her language was. And some other things that I would think about that were important there is that we really kept it focused on the scientist. Every other part of the space program was just kind of in the background in our show. You had no chisel-jawed astronauts or anything like that. It was all about the science. And more importantly, how the science was embedded in those people's lives. Again, she was a mom and she was a wife, but her science was so important to her and it really drove the way she saw the world. And so when you watch interviews of Katherine Johnson talking about the civil rights movement, for example, you can feel that she's seeing it through this physics lens of pushing back on the world. And I really wanted to capture that in the story as well.
Oh, I love that so much. And before the show, you and I had a chance, we were conversing a little bit about this. And you'd mentioned, how a lot of her work in the mathematics was really understanding how we can manipulate regimes of gravity, for instance, to get astronauts to the moon and back without having to put extra energy into it. And you made the analogy to her own life and what it took for her in her life, and with the civil rights movement and manipulating other regimes to try to put as little energy in as you need to, but still kind of have these major transitions occur.
Yeah.
I really appreciated that viewpoint from you.
Yeah, I think that's something really special about how her work really influenced her thinking of that time too. That you can try to speed around space in a rocket, or you can just make the world a place where things fall more naturally and like she always said, rockets get astronauts off the planet, math gets it back home. And I just love the way she thought about paths and math and life as all of this package.
Yeah. And in the end, we ended up saving 3 people and bringing them home from the moon because of that math. She, worked to make the math that we used to bring those people back. When really, when you read up on Apollo 13, it really sounds like they should not have made it. It was an impressive feat of mathematics and engineering to make that happen.
Like they say, space is hard.
Exactly. Yeah, space is hard, but we're getting good at it, and it's thanks to people like Katherine Johnson who have helped us to get better at it through time. I do want to open it up now to our audience Q&A session to allow those who are watching to ask questions of you. So for the folks out there, feel free. You can drop your questions in the chat right now. Our support staff, Mariam Nassim and Anurup Mahanti, are both standing by to get your questions over. If there are a lot of questions, I promise I'll do my best to get to all of them, but sometimes we can't just because we have so many. And I know many of you are excited to ask Heather all kinds of cool things. And the first question comes from someone who is a longtime fan of our show, Jim Pass, who's also the leader of the Astrosociology Research Institute and often wants to consider, the social dynamic of astrobiology and space exploration. Jim says that astrobiology dominates the search for biosignatures beyond Earth, while the social and behavioral sciences have focused more on terrestrial societies. What lessons learned here do you think can be applied when we start traveling out there to do our work?
Wow, I think what Jim's asking is how do we let sociology, a science that I have no experience in, inform our search for life? And I think a way that I would approach this question might be to say that science and what we choose to do in science is really a reflection of our values. And so when we say that looking for life elsewhere is important, it says something about what we believe, that we really aren't alone and that there is this other possibility out there. And so I see that, if we can make sure that what our search pattern is and where we search actually reflects our values, that's where I see sociology overlapping with astrobiology. I think another thing that I would kind of drill down to in that question is on a more, agnostic biosignatures point of view, or from my science point of view, is like I said, I'm not a sociologist, but I do think about community structure when I look at any sort of assemblage of chemicals or any habitat or potential habitat. The idea that no organisms here on Earth or anywhere are likely doing anything by themselves. We're all dependent on an enormous network of organisms, past and present, that make our life possible. And I think we need a much better understanding of that. I think as people start realizing that they themselves are a biome, this becomes more evident. And as astrobiologists stop just looking for this amazing microbe that can live here or there and understand what network of biology it took to make that place habitable, that becomes a much stronger search pattern when we think of things as communities, an ecological approach to astrobiology.
Oh, yeah, I appreciate that so much. I've talked a lot with Carol Cleland, a philosopher of science, who's considered this a lot too, that you can't just have a hydrothermal vent system ecology occurring because it's connected to so many other things like the ocean around it and so many other living things that have occurred on Earth through time.
Yeah.
We have a question from Facebook from user Tom Caruso, who maybe wants a little bit more of an understanding of what agnostic biosignatures are. Tom has asked if maybe one driving motivation for our missions of exploration should be to search for how systems uniquely harness energy. Is that what we are looking for then to understand agnostic biosignatures?
I do think that's a really astute observation that he's made. And part of, when we think about agnostic biosignatures or really think about astrobiology writ large, it's not just enough to say like, oh, this place on this planet has water and is warm enough. But to also think about what would be a potential energy source here? What would be, the electron transfer chain at this location? Do you have reduced carbon that you could use? Things like that. So yeah, getting a little bit more systems level information about what sort of metabolism would be possible for any place is how I think about it. And, that sounds like it's being very specific and not quite agnostic when I put it that way, except that what I'm really saying is to be aware of these chains, these combinations of energy sources and other, substrates that would actually make a metabolism possible, whatever you think that metabolism is. And there's a lot of them. When I say metabolism, you might just think about your own, but the metabolic diversity of our planet tells us that there's lots of ways to eke energy out of raw materials by life.
Yeah, life finds a way, right? There's lots of metabolisms out there. And Anirudh, who's supporting us for the show, dropped in his own question here. He wants to know a bit more about biosignatures and about detection. He'd like to know, how would we actually make agnostic biosignature detections? What kinds of instruments do you envision us needing?
Yeah. So, in our group, the Laboratory for Agnostic Biosignatures, we have a couple of different things that we're investigating. And we have a couple recent papers that have come out that talk about these things. And some of these tools that we would use are things that are currently developed and are really relying on new interpretive frameworks. So we have a paper that just came out led by a postdoc at University of Glasgow, Stuart Marshall, that's all about new ways of interrogating mass spec data. Mass specs are a mature technology. We've got them. At one point, there was 8 planets or 8 moons or, 8 solar system bodies that had a mass spec going around it. There's something that is a very mature technology, but thinking about particular molecules, or again, back to the community idea, thinking about particular molecules or collections of molecules could tell you much more about life. And not by saying, oh, this is a metabolite or something like that, but just this molecule is very complex and would require an organized system like life to even be produced. Then on the other hand, we've got other, crazier ideas, which are new ways of mapping, say, surface complexity of a particle, or understanding just elemental abundances of particles as a way of detecting another kind of complexity that's indicative of life. So we've got old tools and new that we're working on as part of this. And we're also trying to be, non-selective for any particular analyte type in our group. We want to be able to imagine that we could interrogate fluids as well as rocks.
That's fantastic. And I think, also I think a lot about like machine learning and AI and upcoming processes for automation for data collection, which is necessary because we're in the age of big data and it's getting bigger and bigger, and data analysis is such a huge task now.
And that's something else that I think is really important, especially if there are viewers here who are thinking about ways they can contribute, is that if you think about the data volumes that we generate with these instruments when we send them to other planets, and we're starting to move to farther and farther planets, think about Dragonfly going to Titan, the necessity for having some sort of autonomous science system as part of that lander is really growing, because it's very hard to get that volume of data back to Earth for us to look at it. And a lot of times that instrument is just sitting there waiting for the next thing to be told what to do. And if we had an intelligent system that could help, line up experiments for it while we're waiting for all of that data to download, I think for all of your viewers who are going to get into astrobiology, you're going to be so sad to learn how much we're constrained by just how quickly you can move bytes across space and how big those packages of bytes can be. That's a real constraint, especially for the outer solar system.
Absolutely. Whenever I tune into the Deep Space Network and I see like Voyager 1 communicating back to us, and I think about the data stream, and then I try to compare it in my mind to like where we are with Percy and Curiosity and even upcoming missions that will certainly have even more data collection, not just, tens of points or hundreds of points, thousands of points, but tens of thousands, millions of data points. That's so much data. And so having some automation to process, on the front end before sending data back is a huge task, and one that's very important for all of our explorations.
Highly non-trivial.
Awesome.
That's science speak for super important.
We have a question here from user Jesse Delaplane from Facebook. And so Jesse wants to know a bit about your theater work, and I'm going to change her question a little bit. She wanted to know how your skills in organic chemistry and astrobiology contributed to your theater work beyond clear influences for things like determination of azimuth. I'd like to know, how has theater contributed to your work as a scientist and vice versa?
That's really interesting, and I'm gonna clue everyone in on a little secret about me. I know I said that I didn't go to college till I was 30, but something that's actually a little bit deeper back in my past is that right out of high school, I tried to go to art school, and I didn't last a year. And things that I learned in art really got me ready for science, because in art, you're working with really objective or subjective material, and it's very much based on how do people interact with that material. And so a lot of what you're learning in art school is basically how to accept and give critique. And that's something that has been really helpful for me in science, because science is a activity that is built in a community, helping each other and grow through peer review and also review of our proposals. So learning how to give and take critique has been really helpful for me. When you get back those paper reviews and first you're mad, but then you're like, no, wait, what do I need to learn from this? That's actually a skill that artists do all the time. And they're taught how to do it. And they're taught how to give good critique. And I feel like scientists would be in a much better position if we all had to do a year of art school and learn how to give and accept critique and how to grow from it. Because when we get critiques back from our peers, that's all part of the scientific process, trying to make sure that we fix all those little mistakes that we didn't see there through this community activity of peer review.
Oh, that's fantastic. And I would love for all scientists to have a year of art school. I think taking some philosophy courses is also super important for scientists. And I would hope that, artists out there are also taking some courses here and there in science. Understanding the chemistry of the media that you're using, for instance, is kind of huge. Understanding some of the physics of how we build our graphic design programs and stuff like that. So there's so many awesome crossovers there. I think we're going to go back now a bit into some of Agnostic Biosignatures and Astrobiology. User at gothmusiclatum on Twitter wants to know how we might properly identify life that doesn't have the same chemical requirements as Earth-like life. So, if there is life out there that's not life as we know it, how might we best then search for that life?
Yeah, so that's an interesting question. And I think one thing that I always try to get people to understand when we talk about agnostic biosignatures is when you're dealing with a truly unknown, a lot of times you're not saying like, oh, look, I found a life. It's over there. You're really speaking in probability windows. And so, for example, when I was talking about complexity of molecules, you're saying there's, very low probability anything outside of life made this. And the real business of agnostic biosignatures is narrowing down those probability windows to something resembling certainty through using different methods. And so complementary methods that can help you identify through probabilities. Because, there's a strong potential for misidentifications if you're just using analogy, for example, to life on Earth and not trying to employ this idea of probability. I think another kind of example that I try to give for that is the way people have actually approached finding life in deep time on Earth. We like to think of astrobiology as this new thing that's very cutting edge and, buzzing machines and going to space. But finding life is something that paleontologists have been doing for hundreds of years. And a lot of times we're looking at life that didn't look anything like life looks like now. If you look at the Ediacaran period, there's weird life. Life was hugely experimental and making crazy shaped sea creatures that aren't around anymore. And so when paleontologists would find that, they could say, well, this is clearly not life because nothing I've ever seen looks like this before. We don't have six-eyed creatures that look like a bath mat. But the other more sophisticated sort of agnostic biosignatures approach would be to say, I don't know of any way in geology that sediments would arrange themselves in this way without some sort of outside forcing, some sort of energy that could be life to get them to take this weird pattern that I'm seeing in this rock. And so that's a way that I would encourage people to really think about agnostic biosignatures, that it's not that crazy, that we've had to do it before. And before, when we had amazing, chemistry tool sets to complement finding a strange critter in the rock.
Yeah, I can't imagine some of those like Victorian era paleontologists finding some of these weird structures and being like, is this the butt or the head? What is this that I'm looking at? These are aliens of the deep time, aliens of the past. And who knows what, 10,000, 10 million, 100 million years from now on Earth, what kinds of aliens will exist here then compared to what we think of right now. So I love that approach to kind of thinking not just in scales of space about alien life, but also scales of time and how things have changed and how some people have been thinking about this for quite a long time now in our history.
Yeah, so that mode of thinking is something that we can use in this area as well.
Groovy. So our next question, I'm going to preface just for a moment. It's going to be about Titan. And a lot of folks, they hear like Titan might have life. Titan resembles early Earth, but then they also very rarely will hear that like the surface of Titan is extremely cold. And so if there is a chemistry of life occurring there, it's probably a slightly different chemistry than what we have. And so our next question comes from this month's ambassador, Aranava, who wants to know what kinds of agnostic biosignatures we might expect on an organic-rich, cold moon like Titan.
Oh, that's really interesting. So I think one thing that makes Titan a little bit of a challenging place is because, as you say, it's saturated with all of this organic chemistry that we imagine to be like a primordial Earth. So when we think about this cradle of the origin of life, we might imagine a whole lot of the kind of naturally occurring chemistry that's on Titan. And so then what becomes the real business of agnostic biosignatures at that point is saying, do I see any sort of chemistry that I don't expect here? This goes back to that importance of understanding what is in an asteroid, because there's a whole lot of stuff in asteroids that's also in critters. And so understanding, like, is this whole community of molecules something that I would expect just without having life there? I think another way to think about agnostic biosignatures is by always understanding that you're looking at something that's different than what you expect abiotically. And so, we actually don't know enough about Titan right now to really give us that full picture. And so we'll be thinking a lot about analogy to what we would expect just abiotically. There's lots of organic chemistry that happens abiotically. We can think of stuff going on in, the deep ophiolites in Oman, and, all sorts of strange, submarine sediments, things like that. There's abiotic organic chemistry happening. So we'll really have to deconvolve what we know we would expect. So as you said, it's cold. Do we see something that we think involved heat? Well, there would be a way that we'd want to explore. Could this happen abiotically, or does this depend on that extra energy we call life?
Very groovy. And it kind of makes me think too about, why we want samples from asteroids and samples from various places to analyze, to kind of have a better understanding of some of the abiotic organic chemistry occurring in our solar system, not just on planetary surfaces.
Yeah, I think it's really important to understand what is our inheritance from the universe, because all of this stuff came from somewhere, and then life did a whole bunch of work on it and made a whole bunch of new things, that new structures, new molecules, new patterns in nature that we wouldn't have expected otherwise. But in order for us to really say, oh yeah, this is a thing that came from life, even though I don't know that kind of life that made it, we have to really exquisitely understand that inheritance from the stars.
Absolutely. So our next question comes from Nada Linda of Facebook, and this kind of comes to that then, like our inheritance as living organisms on Earth. We have very much the same chemistry across all of life on Earth. There are some small differences, but all of life as we know it is using DNA and RNA and proteins. We're constructed of cells that are roughly constrained to a certain size. Life as we know it has a lot of similarities. And NATO wants to know from your perspective whether or not there could be other information systems. So, do you believe that DNA will be a common recipe for life in the universe, or do you think we'll most likely find other systems of storage of information? And I would offer also, do you think the same of things like proteins and cells?
That's really interesting. I know there's some really interesting work that people do to try and understand how optimized certain molecules are for their jobs. So, for example, there's work that shows that it would be really hard to make a molecule as good as, or not a molecule, macromolecule, as good as ribosomes for doing the job of ribosomes. So if you had an information system that used amino acids like ours, and then was complementarity with DNA, you would probably have a ribosome. So I think that that's one way to look at it. Like, try to think about optimization of structures and macromolecules. Is there a potential better way? I think the one thing that's a little bit worrisome when you do that is whenever you're thinking that something is optimized, you're making a value judgment. And everything about our biochemistry has been influenced by the history of this planet that we're on and the raw ingredients we've had available to us. So my caution about all of that, and this is kind of an answer, but not really, is to always be thinking about signals of life in their planetary context. The one way you could think about DNA is that there's a lot of the raw ingredients for DNA that come to us in meteorites. There's things like nucleobases. So just try to open up your mind to, in another system, though, what possible chemistry would have happened with those raw ingredients. And it may be DNA-like.
We have so many more questions. I do want to pop one of my own in real quick, following on with that, because often I think about origins of life on Earth, and I wonder, could there have been multiple origins of life? Were there multiple life forms? And did the stuff with DNA and proteins and ribosomes just eat everything else? I wonder what your vision of the earliest life on Earth might be. Do you think it was something like multiple forms of life, kind of doing all these different energy transitions? What would you envision for early life on Earth?
I think um, I'm going to answer that by augmenting that, which is to say, why do we think there was only one time period where life was originating? What would keep us from thinking there's maybe not a new kind of life originating right now in some far-flung weird part of our planet that's a little bit chemically different from us, that would have a different set of constraints that a different system might be more amenable to? That's something to think about. It may have not just been one event. And so when I also think about the origin of life and that sort of thing, I also think about the fact that we've had billions of years of history, and there's every possibility that there are things that aren't quite related enough to us that we don't have the tools to see. So sometimes when we're thinking about life that's a little bit different from ours, we should be thinking about here on Earth. If you've heard recently about this virus that has slightly different DNA than we do, is that a new life form? How do we decide if that is? That's a really intriguing question. So I think my answer to that is I don't really think about the origin of life, but the origins of life, and the fact that that could be a contemporary activity as well as something in the distant past.
I love it. And so that kind of feeds into our next question. So T Vent Reedy on Facebook wants to know about the concept of panspermia and this idea that maybe life didn't have an origin at all here on Earth, or at least the main origin here on Earth. Maybe there were origins on Mars, origins on Venus, and other worlds that kind of came here later, or born on rocks. T Vent wants to know then, bringing samples back from something like osiris-rex, do we expect there could be signs of actual biosignatures, agnostic biosignatures from osiris-rex?
I don't really look at osiris-rex that way, or Bennu that way. I really look at that as understanding what is our abiotic background. And, I think, maybe that's sad to know that I don't necessarily think that could be something living there. But space is a really terrible place. And so the kind of constraints that you would have to deal with on a rocky body hurtling around in the solar system for billions of years, where there's not a whole lot of protection, there's not a whole lot of water, there's not a whole lot of weathering, making anything particularly available to you if you are an organism, added on to the fact that you're exposed to all of this cosmic radiation. It's a tough life if it is one. So I think that's part of the motivation for not necessarily thinking there's something on those rocks. And I think the other thing that I would always get people to remember when you're talking about something like panspermia is the pathways that these rocks are taking through the solar system. It's not necessarily a highway to a planet where life hops off at that bus stop. We're part of these enormous ellipses in space that aren't necessarily colliding in the way that you would imagine if you were trying to think about a galactic pathway for life.
Oh, that's so cool. Heather, it's been so much fun having you on the show. I knew I would just get my little nerd tingles going on over here, thinking about agnostic biosignatures and rock operas and all of this cool stuff. For those who are watching, what do you think when you hear agnostic biosignature? What do you want to explore in looking for potential signs of life, or in doing physics detections out there in the cosmos? Let us know on Twitter and on our other social media. On Twitter, you can find us at NASA Astrobio and at SEG.org. You can certainly reach out to myself. I'm sure Dr. Graham would love to also continue the conversation with you online in the public arena. I do apologize I couldn't get to all of the questions, but there were just so many good ones. It's so hard. But Dr. Heather Graham, thank you so much for joining us for Ask an Astrobiologist.
Thank you so much, everyone. It's been a pleasure.
It's so great having you on. For those who do want to stay in the loop with our show or other events and activities going on through NASA Astrobiology, including things from the Laboratory for Agnostic Biosignatures or the Network for Life Detection, you can sign up to join the email list from NASA Astrobiology. And so, once again, thank you, Dr. Heather Graham, for joining us. Thank you, everyone, for watching. We truly appreciate it. And until next time, remember, stay curious.